Hello to the people in the recording. I forgot to press record, so I'll just super quickly explain what we're doing. So we're doing the Hell-Volhard-Zelinsky reaction, where we start with the carboxylic acid, and we have two different conditions. So for the first one, we have Br2, PBr3, and H2O. For the second one, we're missing the H2O. So I'll have you guys remind me, what does Br2 do? I know it says it on the board, but the Br2. It puts a Br on the alpha carbon, and then the PBr3 turns OH to Br. Cool. So we have the intermediate. For the second reaction, we're done. That's all we can do. So this is our final product. For the top one, we have H2O left over. And now that we can visualize the intermediate, H2O can react with this guy because it's a what functional carbon? Acyl halide. Cool. And how reactive are acyl halides? Very, very, very reactive. Cool. So if we have this super reactive compound and we have H2O present, the H2O is going to replace the Br for an OH. So we're going to turn it back into a carboxylic acid. So I'm going to zoom out just a tad. And we keep this part of it exactly the same. And we exchange the new Br for an OH. So just to recap this reaction, if we have H2O present, go back to an OH for the final product, we only add one bromine. If we do not have H2O, we're going to end up with two bromine. Yes. Yep. Yes. So yes, you can definitely say that, but also the first thing you want to think about is you can only add it to the alpha carbon. And in this case, we only have one alpha carbon. So in general, yes, you always add to the more substituted alpha carbon. In this case, we only have one. Yes. It could, well, this one is secondary, but it could have been tertiary. It just won't really be like fully substituted or quaternary, you know what I mean? Because then it would kind of be pointless. You can't add a Br. So, but it definitely could be different than the one I gave you. Yes. Not always. So the alpha carbon is just defined as the carbon that is right next door to the carbonyl. So it could be primary, secondary, tertiary, quaternary. It could have any number of hydrogens on it. I just chose to draw this one just because that's the one that Dr. West lectures and you guys are asking very, very, very good questions. I love to hear it. So any more questions on this reaction or anything we've done previously? How you first? So that's a really good question. In case anyone didn't hear it, the question is, for the top one, why do we have to add both of those BRs and then go back to the OH? The reason is really just, I have it drawn all as one mechanism, but usually if you were actually doing this in the lab, you would first just add Br2, and then you would just add PBr3, and then you would just add H2O. So it's not like the molecule chooses to react that way necessarily, but that's the order that we put the reaction. If we just had all this stuff in the mixture, it honestly wouldn't even alkyl halide because, or an acyl halide, because it's just, that would be too unfavorable. That's a really good question. So Bella and then Barry. It is. So the alpha carbon is anytime we have a carbonyl. So this is like the important carbon. This guy is the alpha. This is beta. This is gamma, so on and so forth. Yes. Yeah, so on both sides it'll be alpha, but in this case, we don't have a carbon on this side. You are so right. I did the colors backwards. That's my bad. For a second, I was so confused. I was like, what are you talking about? That was my B. Yeah, theoretically, I guess it could also be chlorine, but in this class, we just do PR. Okay, so I'm very sorry about the color thing. I see why everyone was confused now. Does this look a little bit better? Okay, cool. And then was that your question, Erin? Okay, cool. Awesome. So just want to make sure we're good with this. I'll leave it for another second, and then we shall move. So the next thing we're going to do is the alkylation reaction. So the alkylation reaction is something that we've heard before this semester. What other reaction was called an alkylation? The Friedel-Crafts, and yes, it was the alkylation, but I mean, like, what was happening in the reaction? So it was Friedel-Crafts. So what was the nucleophile? The benzene. So in all of the electrophilic aromatic substitution reactions, benzene is always the nucleophile. What was the electrophile? So the acid was the catalyst, but what was the other reactant? Something halide. Alkyl halide. Come on, guys, you don't remember? So it looks something like this. Right? So both of those guys are called alkylations. So if he just said do an alkylation, how would you know which one you're doing, right? Well, the biggest indicator is one, the AlCl3. So only the Friedel-Crafts reaction has AlCl3. And then also, you know, it's a chapter 18 alkylation if he gives you a ketone or an aldehyde. And you know it's a chapter 15 reaction when he gives you a benzene ring. So that's kind of how I want you guys to think, like, when we talked about BR2 and the algination and everything. So do you see where I'm comparing and contrasting? Cool. So I will leave this up in the, okay, or not, whatever. So for this chapter, we're going to look at what they give us and how we can do what we do. I don't know what I'm saying. I'm going to draw the hydrogens and be quiet for a sec. So we have alpha 1 and alpha 2. Which one are we going to steal a hydrogen from? The second one, because it is secondary, it's more substituted, so that guy is more stable. So what's going to take the hydrogen? The oxygen. Perfect. That is a perfect answer. So specifically, this oxygen is going to act like a what? Base. Okay, cool. So yes. So let's recap. I'm sorry, I didn't mean to make fun of you. So anything with a negative charge is a base or a nucleophile. Cool. So how do we know? You said base. Oh, no, you said nucleophile. So technically it has a negative charge. So a lot of people would say this is a nucleophile. But we have an acidic hydrogen present. So all this guy wants to do is take its hydrogen and run. It does not care about attacking. It doesn't want to add to the molecule. It's just going to take hydrogen and go. Now we get a negative charge on the alpha carbon. And what have we made now? The enolate. Perfect. Question. Yeah, so at this point, you could have pretty much used any base you want. It's just common for some reason for the alkylation for them to give you some kind of alkoxide ion. But you could have used NaOH, Cl minus, anything negative pretty much. All right. So now that we have a negative charge on our carbon, this guy is going to act like a what? A nucleophile. Now we have the nucleophile. Cool. So the electrophile is going to be the alkyl halide. And this is like an SN2 reaction at this point. So we're going to go in, pack, and kick off the leaving group, which is cool. And again, this is one of those times where I say, like, count your carbons. You have 1, 2, 3. So if we have a 3-carbon chain that we're adding, what's the name of the group we're adding? A propyl chain. Dang, I'm so proud. Okay. So we add we have an H already. And we're going to add a 1, 2, 3 carbon chain, aka a propyl. Ta-da! We are done. Exactly, yes. That's a very, very good point. So since we said this was SN2-like, and it's not exactly an SN2, that's why Dr. Weiss will say SN2-like mechanism. But the main takeaway is that it happens in one step. No reaction. Yes. So it could happen again, but it's not as favorable as the halogenation reaction. And the reason is we added an electron donating group. It's very weakly donating, but it is donating. So in this case, we're not making the other alpha carbon, or excuse me, the other alpha hydrogen more acidic. So it's going to be much harder to take that proton. So if we wanted to make this happen again, we would have to add more catalyst and more energy to make it happen. So theoretically it could, but in this class, we're just going to do a one and done type deal. Now they're asking such good questions. I'm loving it. I'm so happy. All right, so I'll leave it up for another second. This green is obviously not the answer to the question that's up there. That's just what I was writing before. Seems like everyone's good, so we're gonna scroll. And the question that is supposed to be for this, I don't know why the thing got messed up, but the question is, what is the major product of this reaction? So we have LDA. Does anyone know what LDA is? Cool. So all you need to know is that it is a bulky base. So I'm gonna leave you with that. I'm gonna give you 3 minutes-ish to work with the people around you and try to come up with an answer. And then we're gonna go over it together. Okay, so we're going over the answer now. And someone gave a really, really good response. So I'm just gonna draw out what they were saying. So they said that alpha 1 was more substituted, so that's the better hydrogen to take, whereas alpha 2 is less sterically hindered, and that might come into play because we have a bulky base, and we specified that this one is in fact bulky. And they said that they were stuck between A and C, and I think that is a wonderful way of narrowing it down, or like great place to narrow it down to. So we got rid of B, D, E. I would ask you guys what you did, but I've already started this one. So what the heck is this, right? That's not what we're doing here. Cancel that out. We completely lost the carbonyl. Why did we do that? Completely cancel that out. And then this guy added to like the beta position. We don't want that. That sucks. Get rid of that too. So now we're stuck between A and C. And the difference between A and C, as you guys explained to me, was in answer choice A, we added our group to the less substituted alpha position, whereas in C, we added it to the more substituted alpha position. So usually, if I had any other base, which side would we add it to? C, or alpha 1. Cool. But in this case, if he gives you a bulky base, we would go to the less sterically hindered side. So the only time we pick the less substituted carbon is if we have a bulky base. And you might be thinking, what is considered a bulky base? Just LDA. So that's going to be our bulky base for the semester. And I will just write down that bulky base equals add group to less sub side. And another thing that they said that was really good was that that guy is just a base. So it's not adding anything directly. It's just taking a hydrogen. So maybe there's some kind of way we could take the less substituted hydrogen, but then shift it around. But we're not going to do all that. We're actually going to keep it simple for this reaction. So bulky base, add directly to the less substituted side, which would be A, aka alpha 2. So any questions about this one? So if I gave you NaOH or any other base, what answer would you pick? C, but since I gave you LDA, we're going to pick A. Yes. He could, depends on what he says in class. I'm going to leave it to yes, but only this, but one semester he also added like tert butoxide to that list, but he hasn't done that since. So we'll see what he says in class. Seems like we're all good. Questions, comments, concerns? All right. So kind of lied to you before. I don't think we're going to finish chapter 18 today just because the last two things that we're going to do are actually really long. And we're going to shorten them down and do like summaries of it, but I don't want to start it with 10 minutes left because I feel like we'll be rushing really hard. So instead, we're going to do some practice problems. Yay. Yay. All right. Please open properly. I know it won't. Nope, that's not what it was. That's what it meant. Aha, it saved properly. Okay. So we're gonna go down to here. So which of these guys is a keto-enol tautomeric pair? Ooh. So I'm gonna give you a second to look at it. Okay, so I can hear you guys like reasoning out and doing the question. I absolutely love when I just hear people, like, instead of like drawing or whatever, they just go, okay, well, I can narrow it down. It's not one, it's not three, whatever. So we're gonna talk about it like that. So it's not one, and it's not three, because an enol has to have an alkene and an alcohol. This guy doesn't have double bond. This guy has two alcohols, so we get rid of those answers. And then we also, yeah. So it is going to be two, and the reason it's two and not 4 or 5 is because for an enol, the double bond has to be going from the carbonyl carbon to the alpha carbon, or in this case, we just look at it this way, the alcohol carbon to the next door carbon. This guy's too far away, this guy's too far away. So the answer has to be 2 or B in this case. And we're asking for the keto tautomeric. It says which of the following is a keto-enol tautomeric pair. I just couldn't fit it all in one. Any questions on this one? Okay. We're gonna skip that one for now. Okay, so I feel like we've done this one before, but that's okay. So which of the following would undergo racemization in base? And that's word for word what the question asks, so I'll repeat it. Which of the following will undergo racemization in base? So you guys can think about it. While you think about it, I want you to let me know what is required for a racemization. Yes, so an alpha hydrogen on a chiral alpha carbon. Perfect. So look at this for a couple seconds and someone tell me it. 3. Okay, cool. So you guys did that really fast. I'm very proud. So the reason it's 3 is because we have an H, we have an ethyl, we have a methyl, so that guy is chiral. This is one of those ones that he puts wedges and dashes just to trick you. So all 3 of these guys are methyl groups, so that's not even chiral. This one's not chiral. And then this one is chiral, number 2, but it doesn't have a hydrogen present, so that sucks. So the only answer we have is C. There you go. Yes. I'm sorry, what was that? Yeah, so you need a carbonyl carbon, but the most important thing you want to focus on, like if he didn't give you a carbonyl, you know that that's automatically wrong, but you need to focus on specifically a chiral alpha carbon. But yes, good question. All right. So, what would be the major product of the following reaction? So, what is the name of this reaction? Halogenation. All right, so I'm going to leave you with that. So, work on this for a minute and tell me what you think. I hear some people saying an answer, so before you tell me the answer, which ones can I immediately kick out? 3, 4, 5. Okay, cool. So those three are absolute garbage. And the reason they're totally trash is one, that added an OH. What the heck? No, that's stupid. This one, I didn't know we were back in chapter 15. What are you doing, bro, right? And then this one just added 2 chlorines and completely got rid of the carbonyl. All 3 of those are burning trash. Absolute garbage. So which one out of these 2 is the right answer? Number 2. And does anyone want to tell me why it's 2 and not 1? Because number 1 added to the beta carbon, number 2 added to the alpha carbon. Perfect. So in halogenation reactions, we know that acid versus base gives you different answers. And I heard a lot of people say like, oh, this is base catalyzed, but then they were like, so why is it that the base versus acid doesn't matter for this reaction? Because there's only one alpha hydrogen. Cool. So if we had base and we had more hydrogens to take, we could do the reaction multiple times. Awesome. Yes, and then that turns into a what reaction? Haloform, yes. So this one is the exact same question. The only difference is he has acid, but is the answer going to change? No. For this one, though, this is another acid catalyst reaction. So I want you to take a minute and take a look at it. These are so fast. Like I can't even take a sip of my drink. Everyone's like, answer. I know it. So which one are we getting rid of? All of them except the right one. I mean, yeah. But so the first ones I would get rid of would be this guy and this guy because what the heck are they even doing? Goodbye. And then you guys were like, obviously it's not 2 or 3 because that's not the alpha carbon. Perfect. So the only one that makes sense is A. Yay. All right, I think we can squeeze one more good one in here. I don't know why this just says P. If it's like that on your handout, it's supposed to say PBR3. I don't know why it's just P. We did that one. No. Okay, fine. Let's do this. So I'm going to give you a quick minute to look at this. All right, so I heard a couple people whispering. So which ones are we going to immediately get rid of? 4 and 5, because look at these disgusting things, right? Like, what did we do here? And then someone also said we can automatically get rid of 1. That is also true because it didn't add anything right here, even though Br2 is the first reactant. So we're really stuck between 2 and 3. How do we choose between 2 and 3? 3, because there's no water. Cool. So if there's no water, we look for 2 BRs. If there is water, we look for 1 BR. And you guys did an absolutely stellar job today. I completely lost what I was doing. Have a wonderful weekend. I will see you next week, and I will send out the stuff during lecture today. I will send you guys an email. Hello.